Hi, in this lecture we're again going to talk about replicator dynamics. And remember, replicator dynamics have this idea in them that the proportion of people playing a particular action at time t plus 1 depends on the proportion that paid out at time t and then the payoff for that action at time t. Now in the previous lecture we talked about replicator dynamics in the context of people playing actions or strategies, so populations of individuals. In this lecture we're going to talk about it in an ecological context. We're going to think about different phenotypes of a species and those phenotypes having different fitnesses, and think about replicator dynamics as a way to capture the dynamics of that population, of a species. So let me explain what I mean. Remember in replicator dynamics there's a set of types, but now instead of assuming a payoff to each type, I'm going to assume there's a fitness to each type. That's sort of how fit the species is, that member of the species is, to its particular ecological niche. And I'm also going to assume that there's some proportion of each type. Well, now what we can do is we can think of the exact same logic. How many of each type are going to get reproduced in the next population? Well, it's going to depend on the fitness of each type and on the proportion, because the more birds there are of a particular phenotype, the more offspring they're going to have. But it's also due to the more fit a particular type of a species is, the more offspring it's going to have. So the fitness and the proportion are going to determine how many there'll be in the next population. Now, one way to think of this is a fitness wheel. So what you can think of is when you're choosing a mate, that there's just this giant wheel here and you sort of spin this wheel of fortune. And so there's a bunch of different types. There's type 1s, type 2s, type 3s, and you spin the wheel and it stops on type 2. Now the probability it stops on a type 2 is going to depend on two things. The number of 2s, so there's only 2 of them, and the fitness of 2s. So the reason we call this a fitness wheel, and not just a wheel, is the size of the pie here, you can think of as being proportional to the fitness. So the more fit you are, the bigger your slices. So 2s are fit, so they get really big slices. 1s are not very fit, so they get small slices. But then it's also the case, the more of you they are, the more slices you get. So there's lots of 1s, there's 4 1s, so they get more slices. Well, this fitness wheel, quote-unquote, metaphor is the same thing as replicator dynamics. You can think of the size of the slice as being proportional to the fitness, and you can think of the number of slices representing the number of species of that type. And this will give you exactly replicator dynamics. Now what you can think of in some sense is bunching those all together, so putting all the 1s in one big slice, all the 2s in one big slice, and all the 3s in one big slice, and then spin the wheel that way, and that's another way to think of these replicator dynamics. Now I want to use replicator dynamics and the idea of the fitness wheel implicitly to explain something called Fisher's fundamental theorem. Fisher's theorem is going to be really cool because it's going to allow us to combine a bunch of models that we've already used. So remember we had the model that said there is no cardinal. That meant that there's a lot of variation within a species. Second, we had that model of rugged landscapes. The idea being that, like, when you encode a function, you can think of it as a rugged landscape that you're trying to climb hills. And then third, we've got these models of replicator dynamics. What Fisher's fundamental theorem is going to do is it's going to combine all of these models into one and give us an insight about the role that variation plays in adaptation. Okay, so hang on, a lot going on here. So remember, there is no cardinal. That meant that there's a population of things that we call cardinal. There's genetic and phenotypic variation in the population of cardinals. Now remember, we also had the rugged landscape model, saying that if you think of a cardinal, it could have a fitness, which is sort of maybe somewhere here. If one here will have a fitness of this height, one down here is a lower fitness, this has a fairly high fitness, and this has the highest fitness of all. So we can place different cardinals on the landscape, and different cardinals are going to have different fitnesses. So we could think of then replicator dynamics is saying what's going to happen. You're going to copy the more fit, and you're also going to copy the people who exist in higher proportion. So what we can do is we can place all of those diverse cardinals on one landscape, and then we can imagine that replicator dynamics is going to help us choose the ones that are sort of higher up on the landscape. So here's Fisher's theorem, the idea anyway, that higher variances, if you've got more variation, then you should be able to adapt faster. You should be able to climb the landscape faster. Let's see why that's probably true. So suppose there's low variation. There's very low variation, and now I apply some selective pressure, I can only climb up a little bit. But if there's high variation, then I can climb a lot faster. So the more variation, the more people I've got to copy, the more likely there is to be someone good, the better I'm going to do. So let's do an example and see why this is the case. So let's start with a population that has 1/3 of people with fitness 3, 1/3 with fitness 4, and 1/3 with fitness 5. So note that the average fitness here is just going to equal 4. Well, let's look at the weights. Let's just use replicator dynamics and figure out the weights for each of these different strategies. So the weight on strategy 1 is going to be 1/3 times 3, which is 1, The weight on strategy 2 is 1/3 times 4, which is 4/3. And the weight on strategy 3 is 1/3 times 5, which is 5/3. Well, now let's compute the proportion we're going to have in the next period of each type. So the proportion we have in the next period of each type is of type 1. The proportion of type 1 is just going to equal 1 over 1 plus 4/3 plus 5/3, which is going to be 3 over 12. The proportion of type 2 is going to be 4/3 over 1 plus 4/3 plus 5/3, which is going to be 4 over 12. And the proportion of type 3 is just going to be 5/3 over 1 plus 4/3 plus 5/3, which is 5 over 12. So we're going to have 3/12 fitness 3, 4/12 fitness 4, and 5/12 fitness 5. Now if we figure out what's our new average fitness going to be, that's going to be 3 times 3/12 plus 4 times 4/12 plus 5 times 5/12. So we're going to get is 9 plus 16, which is 24, which is going to 50 over 12, which if we divide through is going to be 4 1/6. So what we get is we started out with an average fitness of 4, we end up with an average fitness of 4 1/6. Let's now do a case where we've got medium variance. So before the pass were 3, 4, and 5. Now the fitnesses are 2, 4, and 6. And let's do the same thing. So what's the weight on strategy 1? That's going to be 1/3 times 2, which is 2/3. The weight on strategy 2 is going to be 1/3 times 4, which is 4/3. And the weight on strategy 3 is going to be 1/3 times 6, which is 6/3. And again, the average fitness here, as before, was equal to 4. So now if we want to compute the probability that someone's going to be of type 1 in the next period, that's just going to be 2/3 over 2/3 plus 4/3 plus 6/3. So that's going to be 2 over 12. The probability someone's of type 2 is going to be, and notice we can get rid of all the thirds here, so that's just going to be 4 over 2 plus 4 plus 6. So that's 4/12, and the probability someone's of type 3 is going to be just 6 over 2 plus 4 plus 6, which is 6/12. So now if we want to compute the new average fitness in this new population, because before it went from 1/3, 1/3, 1/3 to 2/12, 4/12, 6/12, we're going to get that it's 2 times 2/12 plus 4 times 4/12 plus 6 times 6/12. So that's going to be 4 plus 16, which is 20, plus 36, which is 56 over 12, right? And so that's going to be 4 and 4/6. So before we had 4 1/6, now we're going to get 4 and 4/6. Last, let's do a population where we have really high variance. So 1/3 of a pop fitness of 0, 1/3 of a fitness of 4, and 1/3 of a fitness of 8. Again, let's do all the math. Here's what we get. The weight on strategy 1, this will be easy, is going to be 0 because the fitness is 0. The weight on strategy 2 is going to be 4/3, and the weight on strategy 3 is going to be 8/3. So the probability someone's strategy 1 next time is going to be 0. The probability someone's strategy 2 is just going to be 4/3 over 4/3 plus 8/3. So that's 1/3, which means the probability someone's strategy 3 is going to be 2/3. So if we compute the new average fitness, remember before the average fitness was 4, the new average fitness is going to be 1/3 times 4 plus 2/3 times 8. So that's 4/3 plus 16, which is 20/3, right? So what we get is we get the average fitness is then going to be 6 and 2/3. So in the first case, what we get is we got a gain. When the fitnesses were at 3, 4, and 5, fitness increased by 1/6. In the second case, when we had a little bit more variation, the fitness increased by 4/6. And in the third case, when we have even greater variation, the fitness increased by 2 and 4/6. Remember, because the average gain went up from 4 to 6 and 2/3. So what we see is the amount of gain seems to be increasing in the variation. So the more variation, the faster the population can adapt. Well, let's compute the variation in each of these populations. Remember, variation is just the difference from the mean. So in the first case, the variation would be 3 minus 4 squared plus 4 minus 4 squared plus 5 minus 4 squared. So that's just going to be 2. And I'll just do the last one. In the last case, we're going to get 0 minus 4 squared, which is 16, plus 4 minus 4 squared, which is 0, plus 8 minus 4 squared, which is also 16. We're going to get 32. So this gives us the variation within each population. So what we had before was the gain. And if we put this in terms of 6, the gains are 1/6, 4/6, and 16/6. And if we look at the variation, it's 2, 8, and 32. Well, notice, look, this just is 1 goes to 2. This is just times 2. This is just times 2. And this is just times 2. So the gain was exactly half the variation in each case. And in fact, this is Fisher's fundamental theorem. The change in average fitness due to selection, if we have replicator dynamics, is going to be proportional to the variation. So more variation, more adaptation, and they're proportional. And we saw this by combining 3 models. There is no cardinal, there's a rugged landscape, and replicator dynamics. And we get this really interesting result, that the change in average fitness due to selection, due to replicator dynamics, is going to be proportional to the variation. And again, we got it by combining 3 different models. So this is one of the powers of being a many-model thinker. You can then combine them to ask much more deeper scientific questions. But there's a rub here, and this is what we're going to come to in the next lecture. We just got this idea that says more variation is better. But this runs counter to something we learned very early on in the course, which is that you want to reduce variation because of 6 sigma. So what I want to do in the last lecture in this unit is contrast these 2 models. Because when you think about becoming model thinkers, what you'd like to do is have lots of models in your head and use those to adjudicate different intuitions, to figure out which logic applies in which situation. So that's where we'll go next. All right, thank you.